So let's look at second order non-homogeneous differential equations. You might also find to say these can also be called uh, inhomogeneous differential equations. Okay, so we are still using some few concepts that we came up with when we're talking about homogeneous differential equations. We will still need to apply them here, more especially when you're trying to come up with more like a complementary function. Okay, so the idea of non-homogeneous differential equation is that it's just a differential equation that is in the form, let's say you have a constant a d2y dx2, then I'll say plus b dy dx plus cy is equals to f of x. So I believe this rings a bell. When we are talking about homogeneous differential equation, we were equating this equation that we have to what? To zero. But in this case, we're equating it to what? To f of x. Okay. So strictly talking about non-homogeneous differential equations of this kind, uh, it's a situation where our f of x, I'll say f of x is either of these. It's either a trig function. Okay. It's either a trig function, um, an algebraic function, an algebraic function, or we can have a what? An exponential function. Exponential function. So what it is here is that the method that we want to try to use is the method of indeterminate coefficients. Okay, so when you're using the method of indeterminate coefficients, our f of x is either a trig function, an algebraic function, or an exponential function. But generally, a non-homogeneous differential equation is just is that which is equated to what? To f of x, meaning your f of x can be anything. But if I want to use the method of indeterminate coefficients to come up with the solutions of that differential equations, of that differential equation rather, I have to take this into consideration. I have to make that observation to say, okay, am I dealing with a trig function? And that trig function, is it sine, is it cos? uh, Again, am I dealing with an algebraic function or is it an exponential function? But let's say I combine a trig function and an exponential function. Using the method of the indeterminate coefficients might give me a little bit of some problems. So what we are talking about is that we are talking about a non-homogeneous differential equation in general, and also talking about when we use the method of indeterminate coefficients to come up with the solutions of that particular differential equation. Remember to say there's also a method of variation of parameters, which we are going to use for one where we combine, let's say I get a trig function and I get an exponential function, I put them together and let it be my f of x. Then for that I can use the variation of parameters. Okay, so now having said that, uh, once again I'm just focusing on the method of indeterminate coefficients. Okay, but what I'm just going to talk about now is just like the brief introduction of how we go about everything. Then we'll look at some examples in the next video. So make sure to say you watch the next video too. So what it is that when you are given that particular differential equation that you have, the first thing that you have to do, you need to find a solution for the homogeneous differential equation. You are given a non-homogeneous differential equation, but from that non-homogeneous differential equation, you need to find um, the solutions of the homogeneous differential equation, just like I'm given here. That is non-homogeneous, but I'll pick the homogeneous part and equate it to zero. Like I'll pick this part, equate it to zero, meaning it becomes homogeneous. Then I need to find the solutions to that, and we know the steps that we go about, that we use to go about coming up with the solutions for a homogeneous differential equation, of which you just need to come up with your auxiliary equation and determine whether you have, I mean, in terms of m, whether you have real roots, real equal roots, real distinct roots, or you have complex roots. Okay, so now what it is that you'll be coming up with particular solutions. Okay, we'll be coming up with particular solutions. So when we come up with the solutions from the homogeneous differential equation, what we are going to come up with is a function that we call the complementary function. Okay, so at the end of it all, the general solution, which I'll just write as JS, general solution is going to be equals to YCF plus Y PS. So what I mean here by YCF, that is the complementary function. Then PS is the particular solution. So now from the homogeneous differential equation, you come up with this. Okay. Then from this part here, you come up with what? You come up with that. Okay. So now what we do is that for our f of x, for us to use the f of x that we have to determine the particular solutions, here is what you're going to do. At this point, you're going to say your f of x is in these are in pairs, and it depends with the nature of our f of x. So now let's say, for example, our f of x is a constant, like let's say 1. Okay, our particular solution is also going to be like a constant c. Then if it's x, okay, if let's say it's x or something like that, what's going to happen is that our particular solution is going to be in the form cx plus what? Plus d. Okay, what if it's in the form let's say it's a quadratic form of x. Okay, or just say quadratic form of x. The way it's going to be is that this is going to be cx squared plus what? Plus dx plus what? Plus e. Then what if it's in the form let's say a constant multiplied by sine p there, px, or let's say it is another constant, let's say it's r cos px there. Okay, so meaning the particular solution is going to be c cos px plus d sine px there. Then the last one, let's say it is a constant multiplied by e to the power px, meaning our our particular solution is going to be in the form c e uh, okay, e to the px, like that. Okay, so now these are just more like the formats. When you observe what your f of x is, okay, then you're going to relate it to a particular solution. In this case, if it's a constant, you're just going to use c. If it's x, you're going to use what? Cx plus d. Okay, then if it's a quadratic form of x, you're going to use that. If it's a trig form, you're going to use that. If it's an exponential, you're going to use that. So this makes sense to say for indeterminate coefficients, okay, it's either f of x is a trig function, an algebraic function, or an exponential function. Okay, so now what will happen is that when we determine what our particular solution is, okay, we'll have to substitute it in the differential equation that we are given to come up with what? To come up with the indeterminate coefficients. And what are those indeterminate coefficients? Those indeterminate coefficients I'm talking about is simply like the c, the d, the e here, so on and so forth. So when you determine what your yp is, meaning your yps is, meaning your particular solution, substitute it in that. Okay, then come up with what? Whatever that you come up with is going to help you to come up with what? Your indeterminate coefficients. In this case, the c, the d, or whatever letter that you use, it doesn't really matter. It doesn't really make a difference. It's one and the same thing. Now the question is that how do you substitute? So what it is here is that before you even go to that stage of you substituting in this differential equation, you need to compare between your particular solution and your complementary function. If your particular solution is the same or it exists in the complementary function, multiply it by x as many times as possible until it no longer appears to be like a complementary function. You're going to see that in a short while. Let's just say, for example, if our complementary function was equals to, let's say, a e to the 2x plus, let's say, b e to the minus 3x like that. Then I had to find that my f of x, was equals to let's say it was equals to e to the 2x. If this is my f of x, meaning the particular solution, it will take this form. It is going to be what, the y ps is going to be equals to c e to the what, to the 2x. But check something out. This, you have your e to the 2x and e to the 2x in the complementary function and in your particular solution. Those are the same. They are not supposed to be the same. You might say, okay, they are different because I have a and I have c here. But those are just constants. It can be like a 1 or a 2 or something. But looking at an exponential the way it is here, and I also have it the same here, what I mean is that you can observe from the power that they are the same. So what you do is that before you go ahead and do anything that you're supposed to do to make that substitution that you're supposed to make, multiply this by x. So you can make this, I can multiply that by x. I put x there. Okay, let me write it as yps is equals to, it will be cxe to the 2x like that. So if you observe right now, you have like xe to the 2x is no longer appears to be like ax I mean ae to the 2x. So that's the key. If your particular solution appears in your complementary function, multiply it by x as many times as you can. I'm not saying I multiply this by x squared or by 2x. You can just multiply it by an x that is greater than the x that you have in the complementary function. So make sure to say your particular solution does not appear the same as in the complementary function before you continue. Okay. So having said that, uh, how then do we make those substitutions that we are supposed to make in the differential equation to help us come up with the indeterminate coefficients? How we do it is this: when you come up with your particular solution, you need to differentiate it two times. So meaning you need to move from the way it is, that is, you are going to say y prime of what, the particular solution, then you move to the second derivative y prime prime of the particular solution. So meaning, where if the expression that you get for the second derivative of the particular solution, which is this one, you substitute it here. The first derivative of the particular solution, you replace here, then here you replace the way it is as the particular solution. That's what it means. So before you go through that step, make sure to say your particular solution is not the same as, or let me say, does not appear in the complementary function. That is very, very important. That is very, very, you need to keep that in mind always as you solve such questions. So what to happen is that mm, is there anything that I've not talked about? I guess that's all for the introduction. Yeah. So make sure you watch out the next video, where we're going to do some examples, um, where I tried to come up with the general solutions of the general solution of a given differential equation by the method of indeterminate coefficients. Okay, so that's all in this video. Thank you very much for watching.